All right, let's jump right in. Today, we're going to tackle a physics puzzle that at first glance seems absolutely impossible. We're talking about a high-speed jet, a cannon, and the one perfect shot needed to bring it down. So, let's set the scene.
So here's the deal. You've got a fighter plane just screaming through the sky at 500 meters per second. That's over 1,100 miles an hour, at an altitude of 2,500 meters, and sitting directly under its flight path is a cannon. The question is pretty straightforward. What's the time window that the cannon operator has to actually make that shot? It seriously sounds like a scene straight out of an action movie, doesn't it? But wait a minute. As you start to look at this, you realize a few key things seem to be missing. We have no idea what the cannon's firing speed is, its initial velocity. We don't know the angle it's being fired at. We don't even know its maximum range. So how on earth are we supposed to solve this? It feels like we've been handed a puzzle with half the pieces missing. To figure this out, we've got to put on our physicist hats and crack the code. We're going to go over a few key concepts, our tools, if you will, that are going to help us see this problem in a completely different and much simpler light. First up is something called relative velocity. Now, it might sound all technical, but trust me, you experience this every single day. Just imagine you're walking down the aisle on a moving train. To someone standing on the ground, your speed isn't just your walking speed. It's the train speed plus your walking speed. See, it's all relative to who's watching. This simple idea is absolutely crucial. And this slide just nails the point home. If you fire something from a moving platform like our train, its horizontal speed gets a boost or a cut. Fire forward and you add the platform speed, fire backward and you subtract it. But notice, the vertical motion, it's totally unaffected. The big takeaway here is that we can treat horizontal and vertical motion as two separate things. This brings us to a kind of universal strategy for pretty much any projectile problem. Think of it like a detective's toolkit. First, you break down the velocity into its horizontal and vertical parts. Then you analyze them completely independently. You list out what you know for each direction, and finally, you pick the right tool, the right equation, to solve for what you don't know. It's a system for cutting through all the noise.
But okay, even with this handy toolkit, our plane problem still feels stuck because of all that missing info. And that's because we're about to have a huge aha moment. The real solution isn't where we've been looking at all. The secret, it has nothing to do with how powerful the cannon is. Seriously, the speed of the shell, the angle it's fired at, all of that was just a distraction. So the whole point, the crucial insight, is this. The question is really about the time the plane is in a physically hittable position. It's not a question of the cannon's specs, but of the fundamental laws of physics that are in charge here. And here is the trick. The time the cannon shell has to reach the plane's altitude is limited by one thing and one thing only: gravity. So the maximum time available is simply the time it would take for any object to just free fall from 2,500 meters. The same force of gravity is acting on both the plane and the shell in the exact same way vertically. And what that means is that this entire complex action movie problem, it all boils down to one of the very first equations you learn in physics class, the one for distance under constant acceleration. Here, s is the height, 2,500 meters, and g is just the acceleration due to gravity.
So you plug in the numbers. 2,500 equals 1/2 times g, which is about 10 meters per second squared, times t squared. You solve for time, and there it is. About 22.36 seconds. That's it. That's the entire window. No complex calculations, just a complete change in perspective. Wild, right?
This way of thinking, of finding the core principle hidden inside a messy problem, is basically a superpower. So let's prove it. We're going to do a lightning round and tackle a few real exam questions to see it in action.
Okay, first up from the NEET 2019 exam, we're given this velocity vector where the x and y parts are kind of mixed up, and we need to find the equation for the particle's path. Yeah, that looks a little intimidating. But hey, let's use our strategy. Separate the components. The velocity in the x direction is ky, and in the y direction, it's kx, while the slope of the path is just the ratio of those two. Once you set that up and solve it, you find the path's equation is simply y squared equals x squared plus some constant. Done. Next, from 2016. A projectile is launched at a 45-degree angle. What's its angular momentum around the launch point right when it hits its peak? Again, feels like there are a lot of moving parts to track here. So what's the key insight? What's the aha moment here? At the absolute tippy top of its arc, a projectile's vertical velocity is 0,
just for a split second. Its motion is purely horizontal. That simplifies everything. Angular momentum is just its mass times that horizontal speed times its max height. You plug in the standard formulas for those, and you've got your answer.
Last one from 2015. You have two particles spinning in circles, one inside the other. They both take the exact same amount of time to complete one full circle. The question is, what's the ratio of their angular speeds? Now, this one is basically a trick question if you don't focus on the core concept. Angular speed is literally defined as 2 pi divided by the time period, t. So if the problem tells you their time periods are the same, well, then their angular speeds have to be the same too. The ratio is just 1 to 1. Simple as that. So from shooting down a fighter jet to acing these exam questions, the answer so often isn't about finding a more powerful formula, but about finding a more powerful perspective. It really makes you wonder, doesn't it? What other impossible problems out there, maybe even way outside of physics, are just waiting for the right aha moment to become simple?